Okay, thank you very much for coming, everybody, this evening. And today I'm going to be talking about free trade in one of the most important cities in the world in the history of free trade. And last year I gave some talks on trade in Vienna, Belgrade and Skopje. And one of the things I talked about was the supermarket as a modern miracle of free trade. In the 19th century novel The Count of Monte Cristo, the main character becomes the Count, and he has these extraordinarily lavish banquets and these exotic fruits like pineapples. And most people had never seen a pineapple or even heard of one. Yet today, any of us can just walk down to a local supermarket. You can have pineapples, kiwi fruits, mangoes, all of these exotic fruits from all over the world. Today I'm going to talk about actually a different modern miracle of free trade, and that is the smartphone. 2,000 years ago there was an institution called the Great Library of Alexandria, and at the Great Library they sought to compile all human knowledge in one place. There was, some historians say, up to 400,000 scrolls, all in this library, all the scientific theories, the literature, and so on. Yet today, you have the Great Library of Alexandria in your pocket in the form of a smartphone. All the science, the literature, all the recorded music, you have access to it right there in your pocket. And these smartphones today have between 1,000 to 1,500 individual components from at least 200 primary suppliers from dozens of different countries around the world. So it really is a modern miracle of free trade, like the supermarket. So that makes it particularly bizarre that the smartphone has become such an object of fascination for anti-free trade activism. There was a great quote from Commerce Secretary Howard Lutnick on one of the US TV shows, news shows, and he said, I'll quote him word for word, when they asked him what the trade policy was going to achieve, he said, an army of millions and millions of human beings screwing in little screws to make iPhones, that kind of thing is going to come to America. Now, several investment funds actually calculated what this would result in, and probably the most accurate figure is around $3,500. That's what it would cost for an iPhone if that was actually implemented. But as I'll show today, that would just be the beginning of the problems. What I'm going to do today is talk through some of the processes and components involved in a modern smartphone. So since we are here in Amsterdam, I'm going to start with an excellent Dutch company called ASML. And this company is not a household name like Apple or Microsoft, but it actually is the company that makes modern chip production possible. They pioneered what's called extreme ultraviolet light lithography. Now ASML produced the machines that other companies used to then produce microchips. And they only produce around 50 to 60 EUV machines per year. They cost around $150 to $200 million each. And each machine has more than 100,000 components and weighs around 180 tons. So these would allow chip manufacturers to print very intricate circuit patterns onto silicon wafers. We're talking about 2 to 3 nanometer designs. So that's 2 to 3 billionths of a meter. And so extreme ultraviolet lithography then, what is this? Well, EUV uses 13.5 nanometer wavelength light to do this process. And in order to achieve this, what the machines do is they fire these tiny droplets of tin, 50,000 per second, and those are then hit by laser pulses, and each tin droplet has to be hit with 2 laser pulses in succession. The first one flattens it, the second one turns it into plasma at 220,000 degrees C, and that then creates the EUV light that can be used for this chip production. And this light is then reflected using ultra-precise mirrors from another company called Carl Zeiss AG. And so these mirrors are polished to atomic smoothness, So the imperfection tolerance is 0.1 nanometers. So that's 1/10 of a billionth of a meter. So to put that into perspective, if one of these mirrors was expanded up to the size of Germany, the imperfection tolerance in these mirrors would be less than a millimeter. That's how perfect they have to be for this production. And EUV took 20 plus years of development for ASML. Many said it was not possible, but they achieved it. So it's a great victory for entrepreneurship that enables us to have these advanced chips in our phones. But also then we have to move on to the architecture of these chips. And that comes from a British company in Cambridge called ARM Holdings, or ARM Holdings. And they have only 7,000 to 8,000 employees globally. It was founded by Sophie Wilson and Steve Ferber and came out of Acorn Computers. The first chip they designed in 1985 had 25,000 transistors, yet a modern iPhone chip contains more like 20 billion transistors. And ARM pioneered what's called reduced instruction set computing, or RISC. And this involves simple instructions, and each instruction does one small task, and most instructions execute in one clock cycle. So if you compare this with the x86 chip structure that is in your desktop computer, for instance, that's far more complex. It uses what's called CISC, or complex instruction set computing. That would wear out the battery in your phone very quickly. And so around 30 billion chips are shipped every year using this ARM architecture. So we've now got the manufacturing machine and the architecture. What we do now is we move across to Taiwan, the company that actually produces most of these chips, and that is called TSMC. And that was founded in 1987 by Morris Chang. Again, he's not as famous as Bill Gates or Steve Jobs, but he's been just as important in the history of modern computing. And TSMC produces 12 to 16 million silicon wafers per year, and an advanced wafer can hold 600 to 800 smartphone processors. TSMC produce more than 90% of the world's most advanced chips used in these phones. That's chips with less than 5 nanometer nodes. And billions of these transistors are packed onto a chip the size of a fingernail. So to give you an idea of what this entails, it requires extreme precision engineering at a nanometer scale. So there are more than 1,000 manufacturing steps to produce one of these silicon wafers. And the clean rooms required have to be more than 1,000 times cleaner than an operating theatre. So even one speck of dust might ruin the production of one of these silicon wafers. We then move on to the laser which is used in this production, which comes from a company in Germany, this time called Trumpf. And they were founded in 1923. They're based in Stuttgart, still family owned actually, unusual for a tech company. And they produce extreme precision lasers, a lot of CO2 lasers, but they're also pioneers in fiber laser technology, which is at the cutting edge. And this allows the precise cutting of metals, but in particular inside the ASML machine, as I noted earlier, the tiny tin droplets, 50,000 per second, have to be hit precisely with these pulses of laser, 2 per droplet. And it's these lasers from Trumpf that achieve this, so that each tin droplet can be turned into plasma. So this requires nanosecond level accuracy. One mistimed pulse means a lost plasma, means lost production. So this also illustrates that the supply chain is not just global, it's layered. It's not just lots of little components in your phone from all around the world, it's all layered and interconnected. But we'll move on quickly then to the 5G modem chip in your phone, which typically comes from a company called Qualcomm, based in San Diego. So these chips manage global mobile communication. Qualcomm has more than 140,000 patents and patents pending. And it's really what they produce with this chip is the communication brain of the phone. So that involves sending and receiving data through the internet, calls and messages, and managing signal quality and switching between towers. But then we quickly come back to the Netherlands, to another company, NXP Semiconductors, and they produce the NFC chip in your phone. and that's what's used as the payment processor for Apple Pay and so on. Actually, my business in the UK has done business with NXP, and they're an excellent company. And this requires hardware-level cryptography and tamper-resistant chip design, of course, a secure storage layer for payment credentials, and this also all has to happen very quickly. When you're in the shop and you pay for something, it really has to happen in less than a second with these chips. Moving on then to the motion sensors in your smartphone, and these come from a company, typically from a company called Bosch in Germany. They produce MEMS sensors, or micro-electromechanical systems. So these mechanical systems can be smaller than a grain of dust, and they detect movement and orientation. So they produce the accelerometer in your phone, which detects movement. It's the step counter. It's used for augmented reality and so on. And then they also produce the gyroscopes, which detects rotation, is involved in camera stabilization and video gaming, and so on. And Bosch ships billions of these sensors every year across industries. But then what this all requires is power management in the phone. Now, there are a few companies that do power management chips, but one in particular is called ST Microelectronics. They are a Franco-Italian company that's actually based in Geneva. And so these PMICs, or power management integrated circuits, they control how energy flows through the phone. They convert and distribute voltage, and they protect components from damage, often making thousands of adjustments per second in your phone as you're using it. But again, this also requires radio frequency signal management chips, which typically come from a company called Infineon Technologies in Germany. And these are responsible for amplifying weak incoming signals from cell towers, filtering out noise and interference, switching between frequency bands, and managing antenna performance. And for Infineon, the expertise is in high-frequency physics and materials that remain stable under electrical stress. But with all these processes going on in the phone then, what you require is a screen. And these typically come from South Korea, a company you may have heard of called Samsung, who produce around 70 to 80% of the OLED screens, especially in the high-end phones. And these OLED screens, they produce their own light, so no backlight needed. It allows each pixel to turn off and on completely, so you can have true blacks when pixels are turned off. So you actually have much nicer contrast in these modern phones for when you are watching YouTube or whatever it is you want to watch. But then on top of the OLED display, it also requires cover glass, which comes from a company called Corning in the US. And anyone who's read the biography of Steve Jobs may well be familiar with Steve Jobs getting in touch with Corning for the original manufacturing of the iPhone. They produce what's called Gorilla Glass. And the strength for Gorilla Glass comes from a process called ion exchange. The glass is placed in a molten salt bath. Smaller sodium ions in the glass are replaced with larger potassium ions, and this creates compressive stress on the surface. So what that means is this Gorilla Glass is much more difficult to crack, and if it does crack, the cracks then generally don't spread through the glass. What we move to next then is the audio processing chip inside your phone from a company called Cirrus Logic in Austin, Texas. And these chips convert and refine audio signals, so they drive the speakers and the headphones, and they also filter out noise like wind and background chatter when you're speaking on the phone. But all of this in your phone, of course, requires memory. And we then move back to South Korea and Samsung, which have around a 30 to 40% market share in DRAM and NAND memory. You may have seen that famous photo from the 1950s where 5 megabytes of memory was delivered by IBM to, I think it was MIT University, and this had to be delivered by a truck and was the size of several refrigerators and required several strong guys to carry it into the university. Yet today, of course, you can have thousands of photos and videos on just a few square millimeters of silicon. And Samsung have really pioneered layer stacking in NAND technology. So there's 200 plus layers in the memory chips in your phone. But in order to get these photos to store this, you require the image sensor, and these typically come from Sony in Japan, which has a 70 plus share, at least in high-end smartphones, for image sensors. And the image sensor is a semiconductor chip that captures incoming light through the lens. It converts light into electrical signals, and then it processes those signals into a digital photo or video. So these sensors, of course, contain tens of millions or even hundreds of millions of pixels. But then, as well as that from Sony, what it also requires is the camera lens, which comes typically from a company called Lagan Precision in Taiwan. So the lens system is a set of ultra-precise glass plastic elements in front of the sensor that focuses light onto the image sensor, controls sharpness and clarity, reduces distortion, and manages the zoom. Now, when you then think about all of these different processes going on in your phone, one of the other things that's required is capacitors. So your smartphone in your pocket has 1,000 to 2,000 capacitors. A capacitor is a component that stores and releases electrical energy. And in your phone, these more than likely come from a company called Murata Manufacturing in Japan. And they've really pioneered these highly advanced multi-layer ceramic capacitors. So what these do is smooth out voltage fluctuations, filter electrical noise from circuits, and support high-speed signal integrity. So essentially they're like shock absorbers for the electricity moving around your phone. And now we come to the last couple of components then in your phone. There are, of course, the adhesives. And these are typically from either 3M in the US or Henkel in Germany. And the expertise here is in polymer chemistry and controlled industrial application at microscopic thickness. So, of course, what these adhesives need to do is to bond the display to the frame, to seal the device against water and dust, to fix the batteries in place, attach the camera modules and internal components, and also actually to damp vibrations and reduce mechanical stress. So now we come to the final component, which I'll talk about today. Last but not least, the humble screw. Now, I started today with that quote from Commerce Secretary Howard Lutnick saying that millions and millions of Americans are going to be screwing in tiny, tiny screws into iPhones. But even the screws in iPhones are actually very sophisticated. One company doing these is called Sanko Techno, based in Japan. And the screws that they produce require ultra-small thread formation without deformation, consistent mechanical strength across millions of units, and compatibility with automated high-speed assembly lines. So if there's any imperfections in these screws across millions of units of production, it can affect camera alignment, waterproof sealing, device rigidity, and the repairability of the phone. So hopefully that has gone some way to explain to you how the smartphone is indeed a modern miracle of free trade. You have the great library of Alexandria in your pocket, that and more, that and all of the music that's ever been recorded and everything else. Now, as I said, there's actually around 1,000 to 1,500 components in a modern smartphone. That's roughly 20 of them, components and machines and processes that I've described today. But since we're here in Amsterdam, one of the historical centres of free trade, let's hope that free trade can continue so that this technology can continue to evolve with all of these amazing technologies from all around the world. So thank you very much, everybody.